Away we go. Hello, Anatomy Peeps 2020 and 2021. We are in lecture 1.1. So we're going to start by jumping a bit around in these slides. At the beginning of all your slides, you'll see the learning outcomes. These are reflected also in your Martini textbook. But we're going to go through about the first 10-ish, 13-ish slides. And then we're going to jump to homeostasis. And that is going to be the focus of our first lecture, looking at general organization and homeostasis of the human body. So let's get to it. The two words that make up the name of this class are anatomy and physiology. And they are two halves of a whole. Anatomy has to do with structure, as you can see. Structure is what it's made of, what's the organ, what's the tissue, what's the cell, where is it located, and anything that gets associated to it. So that's your anatomy piece. The and physiology, or the and P that goes along with A and P, is functional. So physiology is function. What do they do? How do they work? How do they interact? How does that structure result in a particular function? And that's not only individually, so how does one muscle work, but how do a group of muscles work together? Or how do the skeletal system components, bones, interact with the muscular system components, muscles, and how they make the body work itself. So I have in green that I added on the slide. It's something I often say to my students. The structure is related to the function and the function to the structure, all right? Architecture has a similar phrase having to do with form and function and how they're interrelated. So, the ability to have manipulative digits is a result of our anatomy, the reason we can text and type and sew and all of those things. The way your heart is anatomically structured with 4 chambers results in how our blood is able to be transferred and flow into the heart, to the lungs, and then out into the rest of the body. So form and function, structure and function, anatomy and physiology, they go together in a very significant and important way. And that will be the focus of our entire year's worth of class material. Just looking, anatomy is not all-encompassing. There are many different levels of anatomy. As you can see here, gross anatomy, gross not ill gross, but gross as in big, macroscopic, is basically anything we can see. So we'll look at a lot of gross anatomy throughout our year. Anything we dissect, for the most part, is gross anatomy. And then you have a variety pack of other anatomies that you can read through here. Surface or sectional or developmental, like embryological, clinical, etc. So there's varying degrees of anatomy. And then you have a microscopic level. So you have macroscopic or gross, and then you have microscopic. We won't really look at much microscopic within the systems, we will, but not overall. The two main focuses are cytology and histology. We would normally go through the histological chapter, but we won't this year just because of time, but we will touch base on almost all of those tissues when we get into the individual systems and talk about the organ makeup. So we won't miss out on it entirely, just looking at it as its own separate section. Physiology, on the other hand, is functional, and there are different types of physiology as well. Obviously, at a cellular level, cells function in very specific ways. Organs have their own functions or jobs. A whole system, which we'll look at very quickly as well, and then something called pathological physiology, and that's basically pathology, so disease. How does that impact how an organ or a system works? And we'll reflect on pretty much all of those as we go through the individual systems throughout our year. Some clinical terminology, just so that you're aware, because we will reference it throughout the year. Signs and symptoms. So a sign like a fever would be indicating to a doctor or a nurse that there's something wrong, and that's something usually measurable. A sign, symptom is something usually that is felt, right? Like I feel tired, and I feel my clammy hands, things like that. And obviously there's a whole diagnostic process that goes along with that to determine what those signs and symptoms mean in terms of functionality, physiology, problems within the body. Oopsies, speeding ahead for you. Okay, so very quickly, because this is something that I feel is not too challenging to go through, So just in terms of organization in the body, we start at an atomic level and we get all the way up to the organism as a whole. So in other words, the human body. And basically it's like one of those Russian dolls, which I use this analogy in class, but we won't really do that too much. So you have the big Russian doll, you open her up, and then there's a smaller one inside. And you take her and you open her up, and there's a smaller one inside, and so on and so on. Sometimes they do it with like old Easter eggs, and they get tinier and tinier until you have an itsy bitsy one. So with our levels of organization, our itsy bitsiest level is the atom. A bunch of atoms that combine together, as we know from chemistry, is called molecule. We have many important molecules and many important elements and atoms that make us up. We'll talk about a few throughout the year. Molecules working together and created together give us a cell, and that's our smallest unit in the body. That's still something that has your DNA and has your information. A whole bunch of cells that work together to do a similar function is called a tissue. A bunch of tissues that work together to do a similar function is an organ. And a bunch of organs that work together to do a similar job is an organ system. And then all of the 11 organ systems in the human give us the human body or the organism as a whole. And you can see through the slides on your own time, you can see that progression in visual form of those different levels until we get to the whole human body. Okay. Last but not least, in terms of organization, is we have the organ systems. And that is the integument, the skeletal, the muscular, the nervous, the endocrine, the cardiovascular, at least on this slide. Please do read through the different organs that are associated with these systems and the functions. We will cover the majority of these, but there are a few we will not. We will not cover endocrine for time, though I will talk about hormones. That's what the endocrine system is primarily consisting of, and the organs that supply them throughout different systems, because hormones control everything. Don't believe anybody else. That is the truth. They control everything in the human body. So we will definitely reference them. We just won't look at them as their own system necessarily. And then you have lymphatic, respiratory, digestive, urinary, or excretory, and then the reproductive system, both male and female. We won't look at lymphatic separately, although this year I will say we will probably mention a lot of lymphatic references. The lymphatic system is your immune system. And considering we are currently in a global pandemic, the lymphatic system is definitely something that is of interest to us. So we will do our best to reference that as a class as we go through different systems and we see the impacts that those viruses and bacteria have on our immune system as well as other systems too. We will not cover the urinary system, again, based for time, nor the reproductive systems. You get a lot of that in your health class, and again, for time's sake. Just because we are not covering them doesn't mean you do not need to know them. So you want to know what the system is, what major organs, and what those functions are. So again, do take a look at these individual pieces here that go through, and I'll discuss some of those when we are together in class. So the focus of this lecture is homeostasis. Homeostasis is dynamic equilibrium. It's the way in which the body maintains all of the norms to keep the internal environment stable so that all organ systems can function at their optimum level. The body does this through a series of feedback mechanisms that allow the body to respond to external and internal stimuli and to act accordingly. And we're going to take a look at that right now. All homeostatic mechanisms have three basic components: a receptor, a control center, and an effector. The receptor's job is to receive stimulus. So the body might be impacted by some stimulus. It could be external, it could be internal. But that stimulus is going to be gathered by the receptor. That information is going to be gathered, and it's going to send that information to what's called the control center. The control center, most of the time, but not always, tends to be the central nervous system, the brain. And that control center is going to analyze the stimulus information that is received, and it's going to make a decision about what to do. How do I respond to this stimulus to keep the body working properly or to get it back to normal? And it's going to send that instruction out to what's called an effector. Effectors tend to be glands or muscles. And those glands or muscles are going to respond in kind in order to bring that stimulus's response back to normal, all right, to get that body back to normal. We call those norm values set points, kind of like how you set the thermometer, or excuse me, the thermostat in your house, which is the most common example or analogy for how homeostasis works in terms of feedback. So let's look at this very briefly. You set your temperature 69 or 68 degrees for your thermostat. You have a bunch of people over, when that's okay to do again, and the temperature starts to rise in the house. That is noted by the receptor, the thermostat, the thermometer within your thermostat, which is the control center. And that thermostat has a set value. It also has the capability to turn on and off the air conditioner, which is your effector. It's going to blow the cold air into the house, thus restoring homeostasis by decreasing the temperature in the room. Homeostasis is dynamic, meaning it's constantly responding to change, all right? And so that dynamic response is how we maintain the norm. Because we're constantly being bombarded by stimuli, our body has to have a way to respond to it. And there are two pathways in which the body uses to respond. The most common that you will see or observe in the body is called negative feedback. And when we say negative, we mean that whatever response is initiated by the control center to the stimulus is going to negate what the stimulus is causing the body to do, much like we saw with the analogy example with the temperature. I tend to picture negative feedback as a loop. Here's my norm. Here's, I go too high or above it, and then I make a decision to bring me back. Or I go below it, I make a decision to bring me back up. Either way, I'm making a loop because I'm trying to return to the norm. That's why most feedbacks in the body are going to be negative, because usually most stimuli are going to cause the body to be in a ruckus, and we want to put it back to its set point. There are, however, several examples of this, and you will work through some of those. One of the most common is normal body temperature or body temperature regulation. You can see there's an increase or a decrease. I'm going to have you, you'll pause the lecture, and then you'll answer some questions as you read through this example. Questions you have on it, we'll touch base with when we meet. The other example of feedback in the body is called positive feedback. And positive feedback, they're rarer, but they do occur. Childbirth, labor contractions, blood clotting, those are examples of positive feedback systems. Positive feedback means that whatever the initial stimulus is causes a response, and that response gets amplified, in other words, encouraged to move away from the norm, right? So if you're having a baby, you have one contraction, you don't want to stop after one contraction, you want to get the baby out. So there is going to be a feedback system that's going to amplify and continue releasing the hormone that's resulting in your contractions until the initial stimulus, the baby ready to be born, is going to come out. And once that baby is no longer present, those hormone levels are going to drop, that initial stimulus is going to drop, so then the response can shut off, much like shutting off a faucet. So positive feedback, I tend not to talk about it as a loop, although the terminology is there. I tend to think of positive feedback as linear, all right? You have an initial stimulus, it causes a response, and then we keep amplifying that response until the result we want happens, and then it shuts off. Loops continuously circle around as we bounce up and down, away and back to whatever our set point is. Blood clotting is an example of a positive feedback system. And I'll have you pause and read through this and answer a few questions as you read through, and we'll discuss in class. The video that is embedded in your PowerPoint is something that I'll have you watch before we meet as well. Lastly, there are a few pieces to homeostasis. I've already talked about the idea of dynamic equilibrium. I like this other terminology here, even though they don't bold it, continual adaptation. Your body is continuing to adapt to conditions you put it in all the time. And that is what we need those feedback systems to help us because they are going to allow us to maintain homeostasis. If something doesn't maintain balance, if a homeostatic mechanism fails, that is what we refer to as disease. So pathology has its origins in the body's inability to maintain homeostasis. And so typically we talk about diseases as homeostatic imbalances, and that will be the terminology we will use for the remainder of the year.